Okay, in this video we're going to talk about solving, something that should be very well known to you, but I suspect you might have sort of taken for granted what it really means. So I want to really emphasize this idea of what a solution is. So probably the first time you were solving an equation was like in Algebra 1. You solved simple equations with one variable. And so you learned how to solve equations. You did things like, oh, whatever you do to one side, you do to the other. So you learned all these rules and you were able to solve equations like this. So you would have been able to find that x equals 2 is the solution. And hopefully your teacher emphasized the fact that that means that if you were to substitute 2 back in for x, then that is the value that makes the equation true. Okay, so that's what it means to be a solution. We're looking at the values that make the equation true. Makes the equation true. Okay, so you put a circle or a box around your solution and you happily moved on with your life because you had solved that equation. And maybe one day you were, well, not maybe, you definitely one day were introduced to inequalities, and so the equal sign was replaced with either a greater than or a less than or greater than or equal to sign. And suddenly you were taught how to solve these things. You still did the same sort of operations, subtract 3 from both sides. You were maybe cautioned about, so careful when dividing by a negative or multiplying by a negative number, right? Because that would mean you'd have to switch the inequality. So there were a few little additional rules with solving inequalities, but otherwise they were not so different. So you learned how to solve them, and you would write the solution as an inequality, something like x is greater than or equal to 2. And you wanted to just put a box around it and move on, but your teacher would ask you to graph the solution. And I'm sure that you did. But maybe you didn't really understand why suddenly before we weren't graphing and now we are graphing a solution. And of course, the answer is you can. You can graph the solution to an equality, right? If I want to graph x equals 2, I can go ahead and do that. It is just a single point. That is my solution. And I could graph it. It's just a single point 2. But it's not really very interesting. And it's not really illuminating anything. I don't really have a visual need for plotting a single point. But when we try to graph all of the solutions to an inequality like x is greater than or equal to 2, suddenly we have an infinite number of solutions. We can't write down, okay, well, 2.1 is a solution, 2.15 is a solution, 2.7, 3.6, 100.3. We have just an infinite number of things that are greater than or equal to 2. We couldn't possibly write them all down. So that's not very efficient. So how do we really visually represent the set of all points, all values that make the equation true? Well, we imagine plotting them, but we're plotting like an infinite number of points. So you can imagine if I'm like putting dot, 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 dot all over this. If I fill in all of the solutions with points, I get this sort of shaded portion of the number line, and that is representing the set of all solutions, right? So I'm still looking for the solutions. It's just that the visual shading of those solutions gives me a visual sense of what kinds of things are solutions. But then things got more complicated, and one day you were introduced to things with 2 variables. And so suddenly, instead of graphing on the number line, you're graphing in the 2-dimensional Cartesian coordinate plane, right? In fact, even if you were graphing something that had a single variable in it, suddenly you'd graph in the Cartesian plane and you now suddenly have a whole region shaded. By the way, notice that if I take this one-dimensional equation, right, one variable equation, inequality, I should say, not equation, inequality. And I imagine sort of squishing it onto the one-dimensional number line. I really have these 2 graphs are giving me the same information, right? These are both saying that we're looking for x values greater than or equal to 2. The thing that's different here is that if I'm graphing it in the 2-dimensional plane, right, where this is y and this is x, then I can let y be whatever it wanted. So all of the solutions in 2 dimensions to this equation are all these ordered pairs x, y, and y is totally free. It is free to do whatever it wants. And the only restriction is on x. So we're just looking at all of these x values being greater than 2, but y can be whatever it wants. Okay, so again, shading is still representing the solution, and we're getting a good visual of what's happening. But what about when we had 2 variables, x's and y's? Well, probably the first type of 2 variable equations you studied were lines, right? Linear functions. We talked a little bit about that last unit, how lines have a constant rate of change, right? We compared those to the exponential functions that we studied in the last unit, which were a constant percentage rate of change, right? But Now we're talking about linear again. So we probably, hopefully, I expect that you have seen these different forms of a line and hopefully even learned how to convert between these different forms of a line. So this is all review. But again, your teacher probably asked you to graph these equations. And why are we graphing again, right? What does it mean to graph a linear equation? So again, I want you to think about the idea of solutions. So in order to actually visualize the set of all infinitely many ordered pairs that satisfy this two variable equation, you need to graph it. And by graph it, we mean graph all the solutions to it, right? So here's an example. Say we want to find any solution, just any old solution to this equation, 3x plus y equals 5, right? So pause the video or just think for a second, come up with a solution. So of course, a solution is going to have two numbers associated with it. I can't find a single solution. I'm just looking for all such ordered pairs. So once I choose a value, so say let's let x equal 1. Right? Then I've got 3 times 1. I don't know why that cursor is blinking there. Sorry. 3 times 1 plus y equals 5. So this forces, so if I let x equal 1, this forces y to be 2. Right? That's the point that's going to make that true. So I get one solution is the point 1 comma 2. But is this solution I just found the only one? Well, of course not. There are infinitely, so no. There are infinitely many ordered pair solutions. And I'm specifying not just solutions, but ordered pair solutions, because I really want to emphasize the fact that this ordered pair is a single point. It is a solution. Right? So what are some other ones? Like what if I let x equal 0, just to try another one? That would mean 3 times 0 plus y would equal 5. So that would force y to be 5. So then the point 0 comma 5 is a solution. Right? In fact, there's infinitely many. So again, it's not going to really help me to just try to list all of the solutions to this equation, right? Like an exhaustive list is not a good option. So what we want to do is come up with a visual of what the solution means, right? So if we plot, for example, the point 1 comma 2, there's one point, and the point 0 comma 5, there's another point. Okay, there's 2 points on this well, there's just 2 points. There's 2 solutions. How do I graph all infinitely many solutions? Well, I could keep going through an exhaustive list, right? Like I could make like a table of values. Oops, that's a squiggly line, right? So we have the point 1 comma 2, 0 comma 5. We could pick another point, like if x is 2, then we'd have 3 times 2 plus y equals 5. So 6 plus y equals 5. And so subtracting 6 from both sides, we get y equals -1. So we could keep doing this, but it's going to take an infinite amount of time, right? It's going to take an infinite amount of time for us to get this. But what you should have studied when you were studying linear equations, right? The fact that this was a linear equation, right? It meant it forms a line. So really, once I have 2 ordered pair solutions, I can connect those ordered pair solutions, pretend that's straight, and in fact, that will be a quick way, a super convenient, and I don't want us to take for granted, but a super convenient way to plot all infinitely many points that are solutions to this line, right? So every single dot along this line, so I'm trying to emphasize the fact that every single one of these points along the way are solutions. They are an ordered pair that makes the equation true, right? And the graph is a convenient visual way of doing this, right? So the graph gives us a nice visual understanding of all infinitely many ordered pair solutions to this equation.